Complex numbers. Before we get into complex numbers, we got to get into imaginary numbers. Before we get into imaginary numbers, we have to get to pure imaginary numbers. Before we get into pure imaginary numbers, we have to get into I. What's I? I, square root of -1. Simple. Well, it's not really possible in regular arithmetic, but it's possible because we invented it. Now, evaluate this thing. Rad -25. Alright. Okay, what we do is we split this up into rad 25 and -1. This becomes 5 rad -1. And so the answer is just 5i. You're going to come across that a lot in your solving quadratic equations where the discriminant is going to be some negative number and you're going to have to use the number I. It happens. So a pure imaginary number is any number ai where a is not equal to 0. So what do I mean by that? I mean, what do I mean by that? So ai. So if you have the fifth root of rad 32/7 over 16e to the pi power I, that crazy looking son of a gun thing is a pure imaginary number. Anything where a is not equal to 0. Alright, so that's a pure imaginary number. Alright. So now let's do powers of I. I to the first is equal to rad -1, of course. I to the second is equal to what? Well, let me ask you something. And I struggled to explain this the last time I tried to record an imaginary numbers video, but rad 5 times rad 5, that is 5. Rad 9 times rad 9 is equal to 9. Rad A times rad A is equal to A. With that same logic, rad -1 times rad -1 is equal to -1, not 1. A lot of people come up to people like mathematicians or me even sometimes saying that, hey, I is impossible because rad -1 times rad -1, that simplifies to rad 1 and that's 1. Well, no. There's a specific reason why that's not possible. It's called, I'm not going to even get into it, but just know that I squared is equal to -1 based on that concept. So what's I to the third? I to the third is I squared times I to the first, which is -1 times rad -1. So that is basically -I. So I to the third is just -I. What's I to the fourth? Well, I to the fourth is just I squared times I squared, which is -1 times -1, and that's just 1. So I to the fourth is actually 1. It's an actual ordinary number, which is cool. So what's I fifth? Well, I to the fifth is just 1 times I. Alright, so I to the fifth is I. I to the sixth is what? Well, that's I to the fourth times I squared, and that's 1 times -1, so that's -1. I to the seventh, what is that? Well, that's 1 times -I, and 1 times anything is going to be that, so it's -I. I to the eighth is going to be just 1 because it's 1 times 1. You get the cycle here, right? Every 4, because of that 1 there that's helping us along, this cycle happens every 4 powers. So we can come up with a rule here. For any I to the 4 times n, it's going to equal 1. If n is equal to 1, I to the fourth is 1. So on and so forth, like that. I to the 4n plus 1 is equal to I. That's the same thing as one of these things here. I to the 4n plus 2 is equal to -1. And that's equal to this thing right here. I to the 4n plus 3 is equal to negative I. This thing right here. I to the 4n plus 4. Well, then that just rebounds back to 1, which is this. So those are powers of I. Alright. Let's do one sum with these imaginary numbers, just so you know what the heck that even means. I don't like how I even erased that, so I'm going to completely redo that erasing. Yeah, I redo my erasings. Alright, so what's the sum of negative 25 rad plus rad negative 49? Well, as I said before, we split this up into rad 25 negative 1 plus rad 49 times negative 1 like this. We separate out the I from the expression. So this becomes 5 times negative 1 plus 7 times negative 1. We're going to replace this into i's, so 5i plus 7i's. And what's 5i plus 7i? We can take out an I here, 5 plus 7 out, so our answer is 12i. Like terms, 5i and 7i are like terms. You can think of it that way too. So that's just basic arithmetic, showing that you can add and subtract pure imaginary numbers just like anything else. Okay, complex numbers are 1 part real, 1 part imaginary. It's in the form a plus bi, where a and b are real. They're real numbers. And I is equal to negative 1, of course. That's our definition of I here. So what's a complex number? Alright, 5 plus 4i. That's a complex number. 1 part real, 1 part imaginary. A and b are real. I is equal to negative 1. Negative 9 minus I, that's a complex number for sure. 2 minus 3i, negative 9 plus cube root of 2i. Sure, why not? Just I is a complex number. Hey, hell, 2 is a complex number. Pi is a complex number. E is a complex number. Negative 9 is a complex number. Almost anything can be written as a complex number. Why? Well, take the I instance. We can write it as 0 plus I. Alright, 0 plus 1i, I should say. That's a complex number. It's written in the form a plus bi, and 0 is real, 1's real, I is equal to negative 1. That's a complex number. 2 is a complex number. Oh my god, that's like the 9 millionth time that happened. 2 plus 0i. That can be written as a complex number. E is a complex number. E plus 0i. You know? Just happens, you know? So yeah, those are complex numbers, and we're going to be learning how to do operations with these complex numbers very soon. But I want to leave you off with one more thing. How to graph them. How do you graph complex numbers? Well, we'll call this the real scale. Real axis right here. This is getting really abstract here. We're learning. It's actually fun though. And this is called the imaginary axis. Yeah, I know. This entire thing, you're seeing this and saying, is this even real? What the heck? They have an axis for imaginary. Anyway, so we're gonna count by i's here. I, 2i, 3i, 4i here. Real numbers here, 1, 2, 3, 4, 5, so on. Negative 1, negative 2, you get the point. Negative I, negative 2i, negative 3i, you get the point. So if I wanted to say, hey, dude, graph negative 2 plus 4i. Okay, negative 2 here, negative 2 here, 4i there. Boom, that's your point. Negative 2 plus 4i on the real / imaginary coordinate plane. Alright. Another question people might ask you, I don't even know if they do this in Algebra 2 trig, they might do it in pre-calc though, is they ask you, what's the absolute value of this thing? Absolute value? What the hell? How can you find the absolute value of I? I don't even... Alright, so first thing you do when you do that is, it's actually quite simple, really. I think they should teach it in Algebra 2 trig. Actually, it's not that hard. Anyway, so you graph it on this grid, okay? So, alright, we got negative 2 plus 4i. Absolute value is that distance, point's distance from that origin over here. So what are we essentially drawing? We're drawing a distance formula. Yeah, where that length is 4, that length is 2. So what's the hypotenuse? That's 16 plus 4, which is 4 rad 5. Yay! I mean 2 rad 5. What am I even saying? I can't do math in my head really fast because, yeah, so the absolute value of that, absolute value is 2 rad 5, and that's how you find the absolute value. Yeah, alright. What are we going to do now? We're going to do operations with complex numbers. Alright, whatever. I think I'm just going to skip that, actually, because who needs that? Roots of a complex quadratic equation? Man, who even needs that? It's the same thing. Just use a quadratic formula and just use I. It's not that much different. Sum and product, though. We'll get into that. It's pretty important, I guess. So we'll touch on that a bit.